everybody, my name is Apurva and today I am going to be showing you something in mathematics, a question that I found and I had a pattern. So my mentor gave me this question and this is the question. So say you have people, 4 people in this case, this is my example, person 1, person 2, person 3 and person 4. So how many subsets of people can you make such that no two neighbors are in the subset? So here, so I can put one in one subset, just one in a group, and that's okay because none of his neighbors are here. Okay, that's okay. Okay, I'm just gonna not draw curly brackets, I'll be drawing normal brackets. 2 can also be in the set. So can 3 because none of its neighbors are in the subset. So can 4. Now, in the next thing, we will be putting in groups of 2. This is possible. I can put 1 and 3 together in one group and 2 and 4 because they are not neighbors. But I cannot do any more. 3 is definitely impossible. And I cannot, and if I try doing 1 and 2, this is illegal. No. Because 1 and 2 are neighbors. See, they are neighbors. Basically, if you go to the right of one, the first person you find will be the neighbor, and to the left, the next person you find will be the neighbor. That's the definition of neighbors, because for 2 people you say, hey, why they're not neighbors? Actually, let me just solve this. So, yes. So basically there are 6 combinations. So now, is there a pattern with any of these combinations? And yes, I found out. So what the pattern is, and it was a very fascinating pattern actually. So initially when you do it, let's actually do this. So there's one person at a table. Okay, that's a very small table, my bad, sorry. I'm just gonna change one of the settings. Yes, perfect. So there is a table. Perfect circle, I know, nice. So there's one person at the table. There's only one subset I can make, one person. That's why I wrote 1. So let's call this sequence the table sequence. So I'm going to call each one T. So T1, the first combination with one person, will be one person at the table. How many combinations? How many subsets basically? Let me just undo that. 1, correct? Now if I add a second person here on the opposite end, what you're going to see is that, again, I told you go to this way, the neighbor is 2, go this way, the neighbor is 2, right? So 2 cannot be in the subset with 1. So technically 1 can be alone or 2 can be alone. So T2 is equal to 2. Now I'm not writing T's anymore, but you guys get the point. Next up, okay, wait, let me just undo that. Next up, we add a third person, okay? The circles don't get erased, I mean I can erase it in another way. Now, you know what, I can actually select and move that away. La 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 la. Yeah, let's move that a bit. There we go. Okay, now by drawing, we have one person here, this here, and each one is still each other's neighbors. 3 is 1 and 2's neighbor. 1, 2, and 3 still cannot be in groups together because each one is each other's neighbor. So there are 3. Again, this is all straight forward right now. And right now, let's. Next up is with 4 people, we got the answer as 6. Now 5. Now things started to get more and more interesting. And if you guys realize here, right now we're still doing groups of 2. So 1, 2, 3, you could only put one person in. And 0, negative 1 people for the negative values, they're all 0, 0, 0 trailing. Oh my god. Actually, it's converted that to 0. Wow. Not bad actually. But because maybe I drew the circle. Yes, it doesn't convert once. Anyways. Oh wait, yeah. How will it erase? You need the lasso. Yes, thank you. Okay. So let's just forget about this. So 1, 2, 3, then 6. Now looking at 6, some people might already be feeling something with 6. 1, 2, 3, 6, and I at least felt something suspicious. And I'm like, hey, 1 plus 2 plus 3 is 6. So I thought, okay, maybe the first 3 backing sums other number. Actually, that's not what I first thought. What I first thought is all the numbers behind will add up. So I didn't really guess the next one, but I did. I kind of guessed it was 12. I didn't really know what the next one would be, which is with 5 people. But I realized some other pattern along the way to just confirm and check. Now, here's the pattern I realized. So, what you do is, with single pairs, we get 5, right? So, I'm just writing 5. We need to add up all of these. 5 plus. Okay, now if you realize 1 meets 3 and 4, this is one group. 1, 3 and the 1, 4 group. That's two groups. Okay, two groups, correct? Next up, 2 can also have two groups, 5 and 4. 3, however, can only make another group. Why? Because 3, 1 is already done. Or form that a triangle. A kind of. Oh, come on. Yes, thank God it's recruited. 3 to 4 will give us one group. And then. Actually, wait. No, that's an illegal group. Sorry, my bad. Wait one second. Yes, you can't do that. You can do 3 to 5. Yes, this is legal. That is that one. 3 to 4, they are neighbors. And now 4, these bonds are already completed from that to that. So if you realize the first 2, you can connect to all the non-neighbors. The third one, you get one less. And then the fourth one, you get one less. So does the fifth one. But then they just become zeros in the end. So that's why the answer is 10. And now this should break my theory of being the sum of all the backtracking numbers, because my prediction should have been 12. I didn't really predict it, but I kind of had. At this point, though, I was a little surprised, and I'm like, okay, now we need to move on to 6. Now here's the problem. With 6, you can do something that you couldn't do before. A new era for the numbers. And this new era is where you can make a group of 3. Only 2 groups. 2, 3, 4, 5. Okay, so I'm going to be drawing the triangular groups in red. So first we can let's do the system again. Okay, and so first each solo group, that is 6. Everybody can see that. Then do dual groups. Again, I think that diversion pattern I figured out a bit later. So first 3 groups. I figured this pattern out by now. So 3 groups. Then I can predict 3 because I've seen it with my own eyes. But for your sake, 3 again here. So another 3. And then for this 3, I've already told you 2, because this 1-3 bond already happened, as you can see. So 2, and this 4 will give me 1 because this is connected and this is connected, so it just needs to connect to 6. 5 has already been connected, and etc. So that one will be added. And in this case, I got, well, 6. This is 6, that's 12. 12 plus that is 4. What? Hold on. Oh yeah, right. Obviously, we forgot one last thing. Oh wait, one second. Yes, that triangle. No. We forgot a last thing. And the last thing is the 2 triple pairs. Now let's go to red. So that's why when I added up and got 15, I'm like, wait, no, that's not possible. 1 and 2. Bingo was the name. So that adds another 2 from the triple pairs. So if you add up all of these numbers, 6 plus 3 plus 3 plus 2 plus 1 plus 2, you get 17. And at this point, I am like, wait, what? And at this point, I think what happened is I figured something out, and I'm like, wait a minute. I realized that the sum of the previous 2 numbers gives me 1 less than 17. You see, 10 plus 6 is 16. 6 plus 3 is 9. 3 plus 2 is 5. 2 plus 1 is, well, 3. Well, that's the only exception. And this is the exception. It gave me exactly 3. But otherwise, it always gave me 1 less. Now why was this true? I don't know. And at this point I had actually predicted 28. I predicted it. And indeed, when I did the 7 pattern, and then there's also another pattern I learned along the way with the 3 numbers. Like I did this descending thing with that, it applies to the 3 numbers as well, these 3 groups. How? Well, with 7, you will have this extra digit here, which means that if I choose 1 to connect to 3, from 3 I have 2 possibilities. I cannot go to 6 and 2, and from 3 I cannot go to 4. So I have 5. But actually, no, I can go to 6. 7 and 2 and 4 are ruled out because they are in the neighbors of 1 and 3. So I can go to 5 or 6. So that creates 2 combinations. And then within that, if you do 1 to 4, you get 1 combination. 1 to 5, you have already covered. 1 to 6. So as you can see, it kind of within, and then with 4 groups and 5 groups, it kind of circles inwards. So you can do this definite pattern. This works, I'm pretty sure. And oh god. So what that is the sequence, and if in formal notation, let's take this last one, get rid of this. Oh god, no, it didn't work. Delete. Oh wait, I didn't get rid of you. Bye. So this is in the end formal notation. And this is formal notation. T of n is equal to T n minus 1, and I call this the table sequence, plus T of n minus 2, so that back to previous 2 numbers, plus 1 for n greater than 3 strictly. And it does work for 2 and 1 shockingly, because anything before is technically 0. And it does work for 2 and 1 because 2 will technically be 1 plus 0 plus 1 again, because I wrote that plus 1. But for 3 it just breaks down. Because for 3, it just breaks down. And in a sequence, there usually aren't negatives. The time for 1 and 2, it also brings down. And so for 3, because 2 plus 1 is 3, and then plus 1 is 4. So n has to be greater than 3 for this to work. So this is kind of like a modified Fibonacci, actually. And before I thought of that plus 1, I actually thought of this. I'd actually put T1 here, actually. Because T1 is 1. And so it's kind of like a modified Fibonacci sequence. As you can see, 1, 2, 3 are the initial numbers, unlike before where it was just 1 and 1 in the Fibonacci. Right? Then it becomes 2, then it becomes 3. You add those up, and then that becomes 5. Here it's modified, which means that after this, you take the sum of the previous 2, but then you add 1. Take the sum, add 1. Take the sum, add 1. And as you can see, it gets very different very fast. If I ignore that 1 of the Fibonacci, 1, 2, 3 remain the same, but then that becomes 5, which will become 8. And in turn, we get 13. And as you can see, the gap is widening at a considerable rate. And so, this is kind of like a modified. And at first, I thought it was actually, I didn't think of plus 1. I just thought this plus the first number. That's what I thought. When I decided it was plus 1 because that was never really changing. That's more general, but that's okay. And that's only more general because then for 2 and 1 it kind of works, not exactly. But you should just put 1 anyways. So this is my sequence for the equation, unlike Fibonacci, because Fibonacci is actually extremely close. Fibonacci of any n will be equal to. So actually this sequence is kind of like a very close Fibonacci that I figured out. So yeah, oh god, it even created a triangle. I should really disable that mode again later on anyways. F of n minus 1 plus f of n minus 2. And this is very much true. For n greater than 2 instead of n greater than 3. Oh, I can't get rid of that, so I'm not gonna. For n greater than 2 in this case, but for my sequence it is n greater than 3. Because it relies Even though the first two have a sum, the third number is not 4, it's 3 still. That's why it's not even valid for 3, it's valid for 4, n equal to 4, which gives us 6, etc. So this is the similarity between this and the Fibonacci sequence. Okay, thank you guys for watching. Please subscribe to my channel. Click the subscribe button. It even made a perfect rectangle. Thank you. Yeah, it even makes YouTube logos. Great. I love this. Let me just color this. Okay. So thank you everybody for watching. Please subscribe to my channel. Yeah, the subscribe button is down below there. If you want to support me, subscribe. Like this video. Please do if you like it. And turn on the notification bells so you don't miss out any new content. Okay? You don't want to miss out on the next video. Bye!